The quantum realm defies our everyday understanding of reality. In this microscopic world, particles can exist in multiple places at once, communicate instantaneously across vast distances, and even change their past. These mind-bending concepts have puzzled even the greatest scientific minds. Stay till the end for the most reality-shattering quantum concept of all. And if you're fascinated by these quantum mysteries, don't forget to hit like and subscribe for more. Let's explore the top 10 craziest quantum physics concepts, explained simply. 10. Quantum superposition. Imagine being in two places at once, impossible for us, but everyday reality for quantum particles. This is quantum superposition, where particles exist in multiple states simultaneously until measured. The famous Schrödinger's cat thought experiment illustrates this perfectly. A cat in a box with a radioactive atom could be both alive and dead until someone looks inside. While this sounds like science fiction, scientists routinely create superpositions in laboratories. Electrons can spin clockwise and counterclockwise simultaneously, and atoms can exist in multiple energy states at once. This isn't just a theoretical curiosity. Superposition forms the foundation for quantum computers, which exploit this property to perform calculations impossible for conventional computers. The weirdest part: we still don't fully understand why superposition disappears when we observe particles, a mystery at the heart of quantum mechanics. 9. Quantum entanglement. Einstein called it spooky action at a distance because it seemed to violate the speed of light. Quantum entanglement occurs when particles become connected in such a fundamental way that measuring one instantly affects its partner, regardless of distance. Imagine two coins that always show opposite faces when flipped. If one shows heads, the other always shows tails, even if they're separated by galaxies. The mind-boggling aspect is that this correlation happens instantaneously, faster than light could travel between them. Scientists have now demonstrated entanglement between particles separated by hundreds of miles. This isn't just theoretical. Quantum encryption uses entanglement to create unhackable communication systems, and quantum computers leverage it to perform parallel calculations. The implications are profound. Either information can travel faster than light, violating Einstein's relativity, or reality is fundamentally interconnected in ways we're only beginning to understand. 8. Quantum tunneling. Imagine walking toward a solid wall and suddenly appearing on the other side without breaking through. Impossible in our world, but routine in the quantum realm. Quantum tunneling allows particles to pass through energy barriers they shouldn't have enough energy to overcome. This happens because quantum objects behave like waves, with their position described by probability rather than definite location. When these probability waves encounter barriers, a small portion can extend to the other side, giving the particle a chance to tunnel through. This isn't just a laboratory curiosity. Tunneling makes nuclear fusion possible in stars, powers certain types of computer chips, and even explains how enzymes catalyze biological reactions. Perhaps most remarkably, some scientists believe tunneling explains why the universe exists at all, as it may have tunneled into existence from nothing. The strangest part? The thicker the barrier, the less likely tunneling becomes. But it's never impossible, meaning theoretically, you could tunnel through a mountain, though you'd need to wait longer than the age of the universe for it to happen. 7. Wave-particle duality. Is light a wave or a particle? It's both, depending on how you look at it. In the double-slit experiment, light creates a wave-like interference pattern, but when observed, it acts like particles called photons. Even single photons, sent through the slits one at a time, still form a wave pattern over time, as if they interfere with themselves. This wave-particle duality isn't just for light. Electrons, and even molecules, show it too. The twist? Reality seems to decide only when we observe it, challenging our basic understanding of matter and energy. 6. Heisenberg's uncertainty principle. Heisenberg's uncertainty principle says you can't know both a particle's exact position and momentum at the same time. The more precisely you measure one, the less you know about the other. This isn't a flaw in tools, it's built into reality. It explains why atoms stay stable and why even empty space has energy. Most strikingly, it means the universe isn't fully predictable. Some uncertainty is simply unavoidable. 5. Quantum field theory. What if you're not made of particles, but ripples in invisible fields? That's the core idea of quantum field theory. In this view, everything, electrons, photons, quarks, is just vibrations in different quantum fields that fill all of space. Like waves on overlapping oceans, these ripples create the particles and forces we observe. And empty space? It's not empty at all. It's buzzing with virtual particles flickering in and out of existence, leaving real effects behind. This theory unifies most fundamental forces and powers our most precise predictions, redefining reality as fields in motion, not solid stuff. 4. Quantum decoherence. Why don't we see quantum weirdness in everyday life? Quantum decoherence explains it. When quantum systems interact with their environment, their fragile quantum states leak through entanglement, losing their unique behavior. It's like a pure piano note getting lost in background noise. This happens almost instantly for big objects, which is why we don't see things like cats in superposition. Crucially, decoherence doesn't destroy quantum states. It just hides them by spreading their information across the environment. Some scientists even think our consciousness might rely on stable brain patterns that resist this quantum noise. 3. Quantum Zeno effect. Can simply watching something stop it from changing? In quantum physics, yes, and it's called the quantum Zeno effect. When a quantum system is constantly observed, it gets frozen in its state because each measurement resets its evolution. It's like checking a spinning coin so often that it never finishes flipping. This bizarre effect is real. Scientists have used it to stop radioactive decay and preserve quantum states. Even more surprising, the opposite, the anti-Zeno effect, can speed up change with well-timed observations. These strange results raise deep questions. Does observing something shape its fate, or reveal hidden truths about reality itself? 2. Quantum retrocausality. Can the future influence the past? Some quantum experiments suggest it might. In delayed choice setups, decisions made after a particle's journey seem to affect which path it took. Entangled particles even appear to respond to measurements that haven't happened yet. This hints at retrocausality, the idea that information might flow backward in time. It doesn't mean we can change the past, but it challenges the idea that cause must come before effect. Some physicists argue quantum mechanics works just as well in reverse, suggesting time may not be as fixed or fundamental as we think. 1. Quantum multiple worlds. What if every possible outcome of every quantum event actually happens? That's the many worlds interpretation. It suggests the universe splits into parallel versions each time a quantum choice occurs, each as real as ours. When you flip a coin or make a decision, other versions of you experience the alternate results. This means an endless number of universes exist, each holding different versions of your life. Though we can't observe these other worlds, quantum theory implies they're real. They're not far away. They share our space, just inaccessible after splitting. If true, this changes everything we think we know about reality. What do you think about our video? Let me know in the comment section below. Also, subscribe to our channel before you go. Thanks for watching.